This is Dr. Shiraz Minwalla. He's a theoretical physicist at TIFR. Dr. Minwalla is the recipient of the Shanti Swarup Bhatnagar Award in 2011, and his research focuses on the quantum field theory and string theory. Click on the link above if you want to watch an abridged version of the interview. Otherwise, keep watching for the full interview with Dr. Minwalla. As always, this is Scientines, and be sure to like and subscribe to keep seeing content like this.
The purpose of physics, well, one way of stating the purpose of physics is to try to make a mathematical model of reality. So take the world as we see it and try to model it in mathematics. So to make a mathematical model that reproduces as many aspects of the world as we can capture, and perhaps even more importantly, predicts aspects of the world. So if I tell you what the state of the world is now in my mathematical model, the equations of physics give us equations that allow us to evolve the state of the world now to the state of the world at a future time, and therefore use observations now to predict the future. The mathematical picture of the world was this, that everything in the world is made up of particles. Each particle is at a definite position at any given time. And what there is to know in this mathematical model is what you're supposed to try to understand is to specify the positions and velocities of all particles at all time, at one time. And then the equations of physics were equations that took this information, which is information that's supposed to be given to these equations. That takes this information and then predicts the future with them. So then predicts the positions and velocities of particles at all future times, also at all past times. Okay, so this was the classical model of reality. People realized that this mathematical model of reality was insufficient, was inaccurate. That while it captured reality approximately, it broke down at very short distances. For instance, it was not good enough to describe the physics of the atom. Okay, and people realized that the right way to change the model was this, that to make it a more complex mathematical model. The more complex mathematical model associated not a position and velocity with each particle, but a whole function. This function is sometimes called the wave function. Now, you see that this is much more complicated, because in order to specify everything there is to know about the universe, instead of specifying two numbers, namely the position and velocity of every particle, you have to specify a whole function for each particle. Okay? This was the framework of what we call quantum mechanics. Now, this was a big leap from the classical theory. However, while this was, and there's a great deal of truth to this model of reality as far as we understand. However, already over 100 years ago, when quantum mechanics was being developed, this whole idea of the world being made up of particles whose positions you have to specify was already realized to be inaccurate, even in the classical level. What you had to do is to specify not just a function of the position of a finite number of particles at each time. You now had to specify a wave function for the electromagnetic field, or what we sometimes call the functional. That is, you give me a configuration of this electromagnetic field, and I will give you a complex number that comes out, or a number that comes out. Okay, so the theory of the quantum theory of the quantum version of the theory of classical systems, whose degrees of freedom are not finite numbers of particles, but fields that live in every point in space and time, is called quantum field theory. Okay, so that's one of the things you asked me about. You asked me about quantum field theory, and then you also asked me about string theory. So quantum field theory, as you can see perhaps you can see from my description so far, is already considerably more complicated than quantum mechanics, because you have to specify it's a bigger beast. And yet, quantum field theory proved hard to understand. So the mathematical structures of quantum field theory, at least some aspects of quantum field theory, we understand quite well. But there are many things about quantum field theory that we don't understand very well, even today, even almost 100 years after the invention of this the structure. For instance, one thing that we don't understand so well is the following. it often happens that you can have two different classical field theories whose quantization at different values of the coupling constant produces the same physics. This is really strange because these theories and their classical limits are completely different. Understand what you're talking about when you're dealing with a quantum field theory. You understand some of the rules of the game, but there are many phenomena within quantum field theory we don't understand even qualitatively. Of the forces of nature that we've encountered so far, the one that we first understood, namely the force of gravity, is the one that has proved hardest to make a quantum theory of. String theory is a formalism within which it is proved possible to make logically consistent quantum theories of gravity. And this involves many new conceptual ideas that go well beyond quantum field theory, at least from one way of thinking of the subject. From another way, at least from one way of thinking of the subject goes well beyond quantum field theory. And so string theory or quantum gravity is the attempt to make quantum theories of gravity. As I said, there is one formalism available where we believe that we are able to make logically consistent quantum theories of gravity, which is a great first step. But this formalism is only partially understood, and whether the quantum theory of the gravity of the world in which we live lies within this formalism is currently completely unknown. First answer is the honest one. Okay. The honest answer is that it's unlikely in my life, or perhaps even in your life, it's unlikely that string theory, okay, will have practical consequences for human beings on the time scale of 100 years. Okay. Now you said then, so why should we be thinking about this in our day-to-day lives? You know, it's a wonderful thing about human beings that we don't think only about the things that benefit us. Of course we do, right? Because a lot of the reason we do science is to make our lives easier. But that's not the only reason we do science. Part of the reason we do science is something that I believe must have been true of human beings 100,000 years ago. You know, there is this desire to know. See, you know, all of us at some point or the other have looked up at the sky and felt very small and thought, why are we here? Where did it all come from? How did it begin? Where will it end? You know, these vague questions that we cannot even make precise, but the sense of wonder, the sense of what is the grand scheme of things? And understanding string theory helps us in two ways. A, it helps us understand, hopefully will one day help us understand quantum gravity. Will hopefully one day help us understand how our world works at the very minute level, even if it's just knowing how the world works, even if there are no practical consequences, somehow helps us, right? Somehow satisfies us. And then there are other slightly more well-posed questions that it might help us answer. For instance, all of us have wondered, how did the universe begin? Currently, physicists don't know the answer. Okay? If you take the equations of physics and use them to make a movie of the universe and run it backwards in time, you come to a point where, the point just before the Big Bang, during inflation or something like that, in which this movie becomes grainy. Because the equations of physics that you need to run the movie further back are as yet unknown. So understanding questions like things like about quantum gravity could help us perhaps to answer questions that seem very grand, like how did the universe begin? Sounds like worth knowing. It's worth knowing that, even if it doesn't help us make a better computer. Okay, so that's my first answer. Let me give you a quick second answer also, though, because I've been a bit glib. The second answer is this, that I think that if you asked Dirac or Heisenberg or Bohr, why should we understand how the atom works 100 years ago? What practical benefit will it give me? I think none of them would have had an answer. And yet, the semiconductor industry, for instance, is based on great understanding of quantum physics as applied to the atom. Without semiconductors, we would have no computers, for instance. We wouldn't be able to do this interview. So what's also true is that applications of knowledge happen well after the fact. it's hard to know what application knowledge will have until you have it. And even then, it's hard to know it for a few years. Then somebody sometimes finds an application. Perhaps that will happen to quantum gravity. I don't think it's very likely in the next 100 years. Typically, somebody who wants to pursue theoretical physics starts out as an academic. What that means is that the person, goes to school and college, then does a first degree in which she studies science and physics and mathematics. Then you go on to a next degree, or perhaps directly to a PhD, where you start learning how to do research in theoretical physics. It's the way that works, as you probably know, is that you're associated with one PhD advisor, and you learn how to do research from him or her. You learn how to solve one or two problems really well, and then you take it from there. And okay, one, of course, career option is academics. Right? That's what the system is gearing you towards. And I have to say, academics is, in my opinion, a fantastic life. But if you set out along that path and realize at some point that you don't want it, or you'd rather do something else, increasingly there are many career options for people who have studied theoretical physics in general, or theoretical mathematics. And these options are wide-ranging. For instance, they range from working in a financial company. There are many people who appreciate the ability to deal with equations in a competent manner. So in financial companies, people try to model how markets will go, try to model ways of making money. So that's one thing. Software companies, people doing virtual reality would want this. Facebook might want you. Google might want you. There's banks might want you. There's a range of possibilities, possible career options, I believe, for people who want to move into something else. But if you want to spend your life doing physics, of course, what you should become is an academic. The life of an academic, well, in everything in life, not just in physics, life, it's fun to do what you're doing when you're good at it and when you're suited for it. So now I'm addressing the question to somebody who is good at what she is doing and what is suited to what she's doing, and enjoys it. But if you are good at it, you enjoy it, this is what the life of an academic is. An academic, let's say a theoretical physicist, spends every day trying to understand something new. If I come home after work, many days that I come home after work, I come home feeling really happy because I've understood something I did not know before. I did not understand before. And some days I come home feeling even happier because I've understood something that nobody in the world has understood before. It's a great feeling. It's a great feeling, and it's a life of constant growth, because you're constantly learning. You're constantly understanding new things, trying new ideas, fooling around, doing new things. And unlike in almost any other aspect of life, you have no boss. Nobody tells you what to do. You make your own plans. You choose which questions you would like to answer. You address them using the methods you choose. You make your own path. Sometimes it works, sometimes it doesn't. But you're on an adventure. It's very hard to know. I think it's very hard for a person to know exactly what inspired him or her. But I knew from the time I was 6 years old, let's say, that I wanted to be a scientist, 6 or 7 years old. As you probably know, in India, your life is full of uncles and aunties, and all of whom come and ask you all the time, what do you want to be when you grow up? And I would always, from the time of 6 or 7, I would say, I want to be a scientist and a cricketer. At some point, I dropped the cricket. Okay. So somehow I knew I wanted to be a scientist. It's very hard to know what inspired.
Okay.
Difficult time was when deciding what subject I wanted to pursue my PhD. I was not sure for a long time, and that fixing took me time. Science. I think science, like academics in science, can be a great life if you're suited for it. By that I mean, you should both have interest in it and ability in it. Both are important. Without either, it won't work. Okay. Now, to judge whether you have the interest, well, you know that. To judge whether you have the ability, actually, most of us also, I think, know that. Once you start doing some science, you see whether you can manipulate it, you see whether you can understand what's going on, you see whether whether if you get the feeling, I understand it better than the guy who's written this book. That sort of feeling, you will know. Suppose you're a manager in some company. I mean, it just won't compare. How many professions in the world do you understand? You get deep new insights about mathematics, about the nature of reality, about how things work. And you constantly learn, you're constantly teaching, you're constantly understanding new things up to the time you're 70 or 80 years old. Hey, it's an unusually rewarding field. One which is deeply satisfying. And it's not going to make you a millionaire. It's not going to make you very, very rich. But, luckily society is happy to sustain you in a comfortable way. I think it's a great life. Science, as it's taught to students, is taught as a finished product. And yet one of the first things that you realize when you start doing research is that the way that work is presented in a textbook is really how it is discovered. That's something sort of sometimes useful to keep in mind. Science develops partly by logic and systematic thought, but partly by inspired guesswork, by intuition, and by somehow feeling that this is the right way to go. That's a feeling that's something you don't always get from your textbooks.